So let's continue on with looking at the geologic end of hydrogeology and the effects of geology on important aspects of the flow system. So we looked at the hydrogeologic conceptual model for the Piedmont last time and went through that sketch. The sketch ended up, I saw some folks taking pictures of it, ended up a little bit cluttered. But hopefully it's important, I think, to go through the process of drawing that and talk about what the important elements are. There are some other versions of it that maybe are a little more artistically pleasing. This is the video, and then here's a sketch of the completed conceptual model without having some of the the dimensions and the properties. So what I want to talk about is this part of the conceptual model. Up here is saprolite. Saprolite is weathered out crystalline rock, but it behaves very much like a porous material. There are lots of small pores interconnected, but down here in the rock, in the bedrock, much of the material down here has very, very low permeability, and there's really no flow going through this material. And all the flow is going through fractures. So the fractures are a bit different conceptually than what we've been thinking, because when we went to look at properties like porosity, we put in a representative elementary volume, and we said, okay, we're going to average over that volume and come up with a property that is representative. So, that works conceptually pretty nicely for porous material, but for fractures, well, we just have to take a look at that and see. So here's a conceptual model of some fractures. Here's some of that granite. Here's some fractures, and we put a hydraulic head gradient on it. And what we'd be interested in is saying, okay, this is what we really have, and could we represent this as just a uniform block, like we did with the representative elementary volume before? So in order to do that, we have to look at some things. What are really the characteristics that are affecting what the flow would be in response to this head gradient? And here are some of them. So the aperture of a fracture is how much it's open. So we think of a fracture as it's a break, and there are two surfaces and a gap between them, and the aperture is the width of that gap. So typically for fractures in the subsurface, the aperture is tens to hundreds of microns. So micron is 1,000th of a millimeter. So this is that 100 microns is 1/10 of a millimeter. And so so this range, 1/10 of a millimeter. So 1/10 of a millimeter, you got a feel for how thick that is? So let's see, you want to point to something that's 1/10 of a millimeter thick? Hair?
Probably better.
Hair, I think it's about that. Yeah. So the thing that almost everybody has, although not everybody, is your paper. So regular like copier paper is I think of it in thousandths of an inch. It's about 3,000ths of an inch, and a millimeter is 40 thousandths. So 1/10 of a millimeter would be 4,000ths of an inch, about a thickness of a sheet of paper. So fractures in the subsurface, typically the aperture is about like the sheet of paper, pretty thin, but water can flow through that fairly readily, and that's what's available for the water to flow. So that's going to be important. Also, the fracture density. So, what we might want to describe here is how many fractures there are, but really, that would be a number. There would be like 1, 2, 3, I don't know, 4, 5. But the density is what is the ratio of the length? You add up all the lengths and normalize it to the area. Okay, so that would be the fracture density. How much fracture length per area? These fractures are three-dimensional. So this thing right here is actually kind of, it comes out like this, and they're kind of disc shape in 3D. So fracture density would also be the fracture area, all of these fracture areas per unit volume of rock. You could also think about it as if we drill a hole down here, then we have the fracture intersection per unit length, how many fractures there are per unit length. Okay, so fracture density, we can think about it in several different ways. It's a way to characterize how many fractures there are in a unit, overall in a unit of volume of rock. It's going to have units of 1 over length, right? Because a fracture of length per area, we took these lengths, normalized it to the area, that would have a unit of 1 over length. Okay, so that'll be an important characteristic. And also connectivity. So when fractures form in the subsurface, they start out as a small flaw, small break, and then they grow. But they don't necessarily intersect any fractures. When they're small, they're just an isolated break. And then as they grow, they're isolated until they grow and get big enough to intersect another fracture. So in order to have fractures be important in flow, they have to be connected to form a network that allows the water to flow through them to go from point A to point B. They're not connected. They don't really contribute to the flow system. So here's an example of a fracture that's not connected. And these are connected. So if we're interested in flow from here to here, then this is connected fractures. And the term that's used is a percolating network. So this is a fracture network, interconnected network, and it's interconnected in a way that water could flow or percolate through that network. These are just isolated fractures, and in order to flow through this, the water would have to get through this granite, and it's really hard to do that, so this fracture isn't really going to contribute much. So the geometry of the network and how the fractures are interconnected, that's going to be important. And then also fractures, we think of them as a break, and they break and they're open. I showed you some pictures of open fractures, but once that happens and fluid starts flowing, you can have chemical reactions going on that fill in those fractures. So there could be open fractures that have actually fairly large aperture, but they get filled in with minerals. So I'm sure everybody has seen veins, like a rock face with layers of, usually around here there are quartz veins or calcite veins, so they're like white layers. Those are filled fractures, and they were once open and had flow. Had an aperture that you could have water flowing through, and probably they were connected. They were a percolating network, so water could get to them, and then there were precipitation, and they were filled up. They were filled up enough to bond the two sides of the fracture together. Sometimes you see decorative rock that's in like tiles that have these that have veins in them that look kind of right, so we want to be able to analyze flow through this kind of a system here. So in order to do that, what I want to do is go back to when we first saw hydraulic conductivity. We looked at as kind of an analog to flow through porous material. We looked at flow through circular tubes, and they were small tubes, capillary tubes. And we said, okay, this is an analog to flow through pores. And we had an equation, the Poiseuille equation, that was flow through small tube under laminar conditions. And it looked something like this. Okay, this is an analog to what we saw for Poiseuille flow through a circular tube, and this is written for flux through a parallel plate. So this is the channel through which flow is going, and instead of being circle, these are two planes. And so this is the flow per cross-sectional area through that kind of a conduit. And what we see here, there's the head gradient, and there's the minus sign. So that's akin to the hydraulic conductivity. We can write, if we replace that, then we just have Darcy's law, and this is then hydraulic conductivity. So remember, what's the difference between the hydraulic conductivity and permeability? What that is?
Hydraulic conductivity is dependent on the porous media and the fluid, and then the other one's dependent just on the porous media.
Cool, great. So these are the two fluid properties, unit weight and viscosity. And then remember when we saw Poiseuille's law, we had a 32 in the denominator. And I said that came from the shape. Well, here it's a 12. This is a different shape. So we have a different constant here. And then when this was Poiseuille's law, this was the diameter. So here we have, that's the aperture cubed. And then this is that fracture density. So this is the number of these fractures that we have per unit of length. Okay, so that gives us a length squared term here. Okay, so this is the property of the porous medium, and so is that. And these are the two properties of the fluids. Okay, so the important thing here is then this allows us to take this block and translate it into a block that's uniform that we just represent with K. Okay, and the important thing about that is that this mod flow model that everybody now is getting introduced to, that uses K, uses blocks like this and assigns them hydraulic conductivity. So this allows us to go from a conceptual model that is a block with fractures in it and generate an equivalent hydraulic conductivity for use with things like mod flow. Okay. But we also saw that if we wanted to do this with a porous media that was layered, and we wanted to represent it with a single block, that the layers were going like this. It would cause the hydraulic conductivity in this direction to be greater than that. So it ended up being anisotropic. So we can do the same thing with fractured material and end up with an equivalent anisotropic material. So the important thing here is that this is the conceptual model that we saw. We drew something like this. We had these fractures down here. Drew it yesterday or last time. And then if we wanted to simulate this, we're not gonna represent each one of these fractures generally. A lot of times you don't really know where they are. But what it means is that we can represent it in an average sense like this. So we just forget about the fractures and we use equivalent porous media properties to represent it. So that'll be good because that means we can do simulations of the setting around here, the Piedmont setting, the fractured rock, transition zone, saprolite like we have around here, which we'll be doing here soon. Okay. So another thing that's kind of interesting about the fractured rock is that what happens is that when the rock starts to break, you get a small fracture that's growing, and then it links up with another fracture and another fracture, and they form zones of interconnected fractures. And what seems to be the case is that in the subsurface, there are zones of interconnected fractures that sometimes may go and intersect a stream, but in other cases, they're just kind of isolated and are these permeable zones that are kind of individual hydrogeologic units. So here's some work, or here's a figure from a paper that did a bunch of pumping tests. These are all wells, and they were able to pump these wells and see how the wells were connected to each other. And this is what they came up with for the conceptual model. This is up in New Hampshire, but it's in rock. It's very similar to what we have around here. So it looks like this kind of in perspective, and here it is in plan view. So there are these different interconnected fracture zones that are discrete and have boundaries out here. They're interconnected within here. So this is like an isolated aquifer that is intersected by these wells. So that's going to have important implications for how contaminants move through, how a well will perform when it intersects this kind of a permeable zone. So we'll talk next after the exam. We'll start looking at how wells are created and how we use wells to determine permeable zones like this. But I wanted to show you this as kind of an organizing principle for permeable zones created by intersecting fractures in crystalline rock. Okay, so that's the Piedmont. What I want to do is to take a look at some other hydrogeology, and in particular, I want to move towards the coast, and we've got two other things we want to look at. One is coastal plain sands, silts, clays. So these are clastic sediments, and then also this province here, the Floridan limestone. Okay, so this is the coastal plain, and if we go down to the coast, you're gonna find places along the beach where there's clean sand. There's a lot of wave energy here, and that washes out the fine grained materials. But there are fine grained sediments in the vicinity. Those are deposited in areas where the water energy is lower. So you can see this white streak, that's the beach, where we have sands, clean sands formed, and then back here in the back bays, and also offshore, we have finer grained sediment. Here's a bit of a perspective. The beach, and then continental shelf here, where there's finer grained sediment, and also we don't have a back bay here. This gives us settings for having sands, and this mud is silt and clay, so the finer grained materials. Here's an example. This is a quarry near Aiken, South Carolina. and it's 100 feet thick or so, formation that's largely sand. So these are, in some cases, they're very thick formations that are quite permeable. And in other places, the sands are interbedded with finer grain formations, like we saw those silt clay. So here's what the coastal plain looked like in cross section. This is a cross section here. And there's the beach that I talked about. Here's continental shelf. The water is fairly shallow, and then it steepens, and the water depth gets greater. So the coastal plain sediments that we see on shore is right here, and they're resting on top of these crystalline rocks, like what we have in the Piedmont. And then as we go further offshore, these sediments get a lot thicker. And one of the key concepts to see how these sediments get deposited like this is sea level fluctuations. So everybody's familiar with sea level rise, right? That's in the news. And sea level has risen before, and it's gotten this far inland. So it's gotten up to around Columbia. And then it's also dropped and gotten about this far out. So these are sediments that are deposited in as some cases as beach formations. So the sea level was once up here, and then it was also once right here. Okay, so sea level rise and fall causes the shoreline to move from here to here, and that forms very broad layers of interbedded sand, silts, and coals. So what that ends up with is creating something that is shown schematically here. So here's Columbia and Myrtle Beach and the ocean. And what we have here is maybe four-ish confined aquifers that are really thick here and really continuous. And then as we get towards the coast, we have more fine grained materials that are separating these confined aquifers. But the confined aquifers continue on, and they continue out here where the coastal plain sediments get even thicker. There's also a material up here that forms an unconfined aquifer, superficial aquifer. So we have a much more complex situation here than we do in the Piedmont, because we have these four different, you'll see it's a little more complicated than that. We have multiple different confined aquifers in the coastal plain. So the hydraulic head looks like this. It's higher here, and this is the terminal discharge. Hydraulic head, remember when we were looking at doing flow nets, we saw that the hydraulic head will refract when we go through a hydraulic conductivity change. So it's going like this through the low permeability, and then like that through the high permeability. So this is just the opposite of what we were thinking flow was doing. This is a hydraulic head contour now. The flow is going to be perpendicular. So it looks like that. And then if we put both of them together, we see that we have them perpendicular like they should be. The flow is generally kind of a regional recharge system up here, and then flow down through these confined aquifers And in places, the flow needs to go through the confining unit, so it's coming back up and discharging. In this case, it would discharge to a stream. But here we have flow coming up and then also discharging here to surface water, but in this case, it's fresh water discharging to the ocean. Okay, so that's what the flow system looks like. Some broad similarities to what we see in the Piedmont, but this is a much bigger scale, right? In Piedmont, we were thinking from recharge to discharge was like, what do we say, 1,500 feet, right? Half a kilometer. And here, I don't know, Columbia to Myrtle Beach, I don't know, 100 miles, like that. It's much, much bigger scale.
Are any of these aquifers brackish or saline?
Yeah, so that's a good question. So the water quality here changes. And this is salt water. And these aquifers were deposited in salt water or near salt water. So what happens is that there's salt water at this potential, and there's often going to be salt water in here initially. So there's water that recharges, fresh water that recharges and pushes the salt water out. But at depth, it can't circulate out and push the salt water out. So there's a gradient of the dissolved solids, the saltiness of the water. This is fairly fresh, and then, this is fairly fresh, and then the salt content increases as you go downward. We'll talk about salt as a constituent of water, and talk about how I've got a slide that shows the distribution of the salt in the coastal plain. So we'll see that later. But yeah, for sure, there is a big water quality change. It gets saltier as you go down deeper and as you go further towards the coast. Okay, so one of the things that's happening with this scale is that conceptually we have both regional and local flow systems. So I'm gonna go and just sketch here of what I mean by that. So, what we had before was, we said that in the Piedmont, we had a local flow system, and that looked like this. So the water table looked like that, and flows looked like that. Okay, and then we had another drainage over here, and flows to that one. Okay, so this is the local flow system. Recharge ends up discharging to the local stream. Okay, so let's draw this though in conceptually, just in a broader scale. So here's some different streams, and these will have local flow systems, but the head here is a lot lower than the head here. So what can happen is recharge that comes in here might go to here, or it might even go to here. And so what we have then is a system that looks like this, where they're local flow systems, but in addition to that, there are flow systems that go underneath the local flow system and can go in a broader, more regional sense. Okay, so we could have, basically a system where we have these two things superimposed. That's a local flow system, and then these are regional flow systems. So in the coastal plain, this is what we have in that superficial aquifer, there are local flow systems, but the layering contributes to the development of regional flow systems because we're having recharge here, then this unit here is inhibiting the flow from coming up and discharging to the stream. So it continues further on down. You need a bigger head difference to get across this layer, and that causes the flow system to expand and get to be larger before it comes up through the confinement. Okay, so the layering in the coastal plain promotes the development of these regional flow systems. Okay, so another thing that happens as a result of this layering and as a result of this distribution in hydraulic head is this. So here's a well, and this well there's the flow system. So it's intersecting flow that we have some recharge from fairly far away. And there's the hydraulic head. Okay, so the hydraulic head at the well screen is shown by this dashed line. Okay, so this hydraulic head would have an elevation head of this. Right? The pressure would be 0, so it has an elevation head of it. So that would be the elevation head of the water that's here at this screen. That means when you drill this well, the water would rise up to that level. So that means that if you create a well that looks like this and is completed in that confined aquifer, then the water level rises up to there. And if the well's open, it's going to flow on its own. So it wouldn't need to be pumped. So these layers like this and this hydraulic head distribution ends up generating wells that flow spontaneously based on the hydraulic head distribution. So the layering tends to promote this kind of behavior. It's not required. We have wells that flow like this in the Piedmont, but there are fewer of them, and they tend to be right down near streams. But the effect is the same, and the cause is the same. You have to have a hydraulic head that is above the ground level. So if you can think about it, if you have an upward vertical gradient to a stream, then if you drill down, if you got an upward vertical gradient, of 1%, and you drill down 100 feet, then the head at 100 feet depth would be 1 foot higher than the stream. So that well would flow. And there are wells that flow in the Piedmont, but in the coastal plain, there are more of them and they are bigger. So here's some examples. There's some people there, and you can see big fountains. These are flowing wells. Here's a flowing well. This is out in New Mexico, and this one is, actually, I'm not sure where I found that picture, but it wasn't really showing where it is. But the key thing here is that you see these mountains nearby. This is giving a place where the hydraulic head can be elevated and cause the head of the well to rise up. So flowing wells are pretty interesting, kind of cool effect. What happens though is people find this and they find that they can get water out of these wells without having to pump it. So that's pretty cool. And so then they use that water, that drops the hydraulic head, and then they don't flow anymore. So these, you can see these are kind of these old time photographs. Okay. So that's what all those sirens are about. Okay, so flowing well. Here's what the geology looks like. These are the different geologic units. You have different aquifers and confining units. The aquifers are blues and the reds are the confining units. So this is the what's called the Blackwire River Aquifer over in Alabama and Mississippi. See how it kind of wraps around like a crescent? And actually all of these are kind of crescent shaped. So there's one aquifer, a crescent like that, and this is another aquifer, the Chattahoochee River aquifer. So these things are deltas, just like the Mississippi Delta. There's a river system that came out here and the river meandered back and forth and deposited these sands that formed this aquifer. Same with this. And then there are fine-grained sediments in between that form these confining units at a regional scale. We also have more deltas over here, although they're not shown as well on this map. Okay, so that's the classic coastal plain aquifer. That's an important one in South Carolina. The units can be quite thick and quite permeable, so it forms important water supplies. And there are a bunch of examples of that throughout the coastal plain in South Carolina. The Floridan aquifer, though, this is also important somewhat in South Carolina, but it becomes a really important, very, very permeable aquifer down in Florida. Let's take a look at that. Okay, so this aquifer is formed from limestone, and limestone in the Floridan, a lot of the limestones there were formed from reefs. The reefs are places where there are critters growing that create calcium carbonate for their shells, and that material then is the material that is the solid grains in the aquifer. So here's some rock that is formed from former reefs, and here's a picture of this is a quarry, and here's what that material that's been quarried looked like. You can see these large pores. Here's a vertical tube. These are all corals and other types of animals that live on reefs. They're skeletal remains. So tend to be big pores and interconnected, which is really good for making a productive aquifer. The calcium carbonate is also vulnerable to dissolution. CO2 combines with water to create carbonic acid that will dissolve the calcium carbonate. And this structure here is a dissolution structure where the rock has been dissolved away. So taken together, the areas that are underlain by limestone, because, well, have some very distinctive features because of this ability to dissolve the rock out. These areas are called karst terrains, K-A-R-S-T. And Florida is a great example of karst terrain. So when we think of pores in porous material, we usually think of small cavities. In karst and limestone, they can be very large. Here's a picture of a quarry and a cavity there, cave essentially. Also, what happens in these terrains is vertical fractures. You can see here, these are vertical fractures. And as you go up, the vertical fractures are places where there was increased flow of water downward. That water then dissolved out the limestone and formed sinkholes. So you can see how it kind of opens up and it actually flares back like that. So each one of these is like the root of a sinkhole. You can see they're spaced all along there. Here's another example of a sinkhole, a collapsed structure that caused some problems. You could imagine if you were driving to work, ended up as that person there. Some big problems associated with this that really aren't present in other areas. And there are very cool aspects of these large cavities. People can get in there and scuba dive through. So you can imagine that pores of that size create really, really high permeability structures that are going to have a big effect on the overall flow system. So here's the conceptual model for this area. We've got the water table like so, but we have to put in these interconnected conduits where some of them are roughly horizontal following bedding, and there are also these vertical conduits. Here's some sinkholes. So we've got a flow system that comes in here and discharges, well, some of them are going to discharge to the stream, some of them discharge here. This would be a spring. So in karst rains, one of the features is these really big springs where the water is from these large conduits is discharging. Here's some specs on the transmissivity. I don't know if you remember when we looked at this for Piedmont, but Piedmont was down, I think, a max of 100. This starts at 1,000 and goes to 100,000 meters square per day. And then the well yield, 1,000 up to 20,000 gallons per minute. So 20,000 gallons per minute, that's pretty much just limited by what pumps can do. And that's a super high flow. So here's the summary. These are conceptual models of the areas around here: Piedmont, the coastal plain, and the Floridan karst. And we've got, some features. They're all having infiltration and recharge, and then flow and discharge to stream. So that's kind of a similar concept for all of them. We've got the regional flow system here in the coastal plain, in addition to the local flow system. Similar things can happen in karst. In karst, you can have, these large conduits can go various different directions. So you can have some very, very complex flow systems where the water that's recharging here can be discharging in unexpected areas, in unexpected places because of these conduits that form. And to compare, here's the transmissivities and the well yields. And these are directly following from the differences in the geology. The transmissivity 1 to 100, 500 to 10,000, and 1,000 to 100,000. So a fairly broad range, but also big increases as you go from the fractured crystalline rock into the layered sand, and then into the limestone with these large dissolution conduits. And that also maps into very big differences in the well yields. Okay, that's good. I'll see you next time for the exam here. Very good. Yeah.